So basically what's going to be happening is this. Last time we looked at something like this, right? We looked at this argument, cube root of 8, or not cube root of 8, sorry. It was cube root of -8, wasn't it? And then we found three things, didn't we? It was 1 plus radical 3i, or -2, or what? 1 minus radical 3i. Remember that, guys? And in fact, if you remember, the angles were, this one was 2 CIS, what? 60-degree angle, wasn't it? And this one was 2 CIS 180. And third one was what? 2 CIS, was it 300? 300 degrees, right? That's basically what happened. And then we got these two by adding 360 each time, but we have to divide by 3. So you get to realize that each time we are increasing by what? 120 degrees. And of course, you can see that 120 degrees is in fact coming from 360 divided by 3. Why dividing by 3? Because cube root. Now, why do I want to stay on this topic? Because if I were to give you x cubed is equal to -8, right? Then you will recognize, you can easily find x through this way, through complex polar. And you get to realize that x is in fact equal to these three values. Is that clear, guys? X is equal to 1 plus radical 3i, -2, and then 1 minus radical 3i. If you know the three roots, what does that give you? It gives you the power to factor them. We call that linear factorization. Linear factorization is the exponent of x has to be always equal to 1, right? So in fact, in this case, I can rewrite this one into x cubed plus 8 equal to 0, and I can rewrite this one into, using these three roots, x minus 1 plus radical 3i, and then x plus 2 coming from the second one, right? And then x minus 1 minus radical 3i equal to 0. And this is called linear factorization. Right? Okay. Linear factorization, as I mentioned, is once again, I don't really care about the constant. Making sure, I just have to make sure that the exponent of the variable has to be equal to 1. That's what it means by, hence the linear factorization. Now, but some of you guys at this point might be wondering, hey, mister, I thought I know how to factor this one, x cubed plus 3. I mean, x cubed plus 8. How can you factor x cubed plus 8, guys? Oh, I know that. Now I'm going to move on to the next page, starting from here. Is it okay? Oh, I know how to factor that one, because don't you remember, mister, we learned this one in algebra 2. Did you learn this one in algebra 2 or algebra 1? 2? Sum of the cubes. 2? Okay. Then you should remember what this one is equal to, isn't it? Yeah, so what is that equal to? X cubed plus 8 is in fact equal to x plus what? 2, starting from there, isn't it? And then what's the second factor? X squared plus and product of these two, which is what? 2x. And then last one is what? Square of that one. Plus 4. In fact, we made one silly boo-boo. Here, this sign has to be what? Negative. Would you agree? And some of you guys use the word slope or something. Same, always up, same, opposite, always positive, or something like that, right?
Yes.
Now, so mister, I knew how to factor this one with this one, but what's up with this? How are they relating? How is the blue expression related with this black expression? Oh, wait a minute. Then my job right now is I should be able to manipulate blue and then make it look like black. Is that clear, guys? So what I'm going to do is I'm going to rewrite this one in the front. X plus 2. Is that clear, guys? And then guess what I'm about to do? If you want to multiply 3 term by 3 term, oh my, I have to work with 9 terms. Do you see what I'm saying, guys? It's quite annoying. So what I'm going to do is that I'm going to just rewrite this one into x minus 1 minus radical 3i, meaning I distribute the negative sign here. Can you see that, guys? And then second one here is what? X minus 1 plus radical 3i. Can you see that, guys? I distribute the negative sign on the second one as well. But when you look at, wait a minute, guys. When you look at these two expressions, once again, if I want to just use the brute force, I could do that, but it's a little bit annoying. I gotta multiply 3 by 3, 9 things. I could still do it, but ha 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 ha. The same things are repeating just one too many times. What if I group these two things together? Let me try to show you by the coloring here. First thing is the same, and second thing is the same, isn't it? Except the sign in the middle. Oh, wait a minute. Isn't this a conjugate pair, essentially? They're essentially conjugate pair in a way that I can group x minus 1. Then I have a first thing minus the second thing times first thing plus second thing. Then what I can do is I can do the difference of squares, can't I? So my first one is still x plus 2. Now when I do the difference of squares, then I get x minus 1 squared minus radical 3i squared. Is that clear, guys? Then my first one is what? X plus 2. That's fine. How about the second one, guys? Second one here equals, x squared minus 2x plus 1. Would you agree when I expand the x minus 1 squared? Minus, how about the second one? What is a radical 3 squared? 3. What's I squared? Oh, negative 1. So this one is negative and this one is negative, makes it into positive plus 3. Wait a minute, guys. Can you see that this is in fact identical to this one? So, what this one tells us is that the polar representation of complex numbers, in fact, can help us to factor. That's quite odd. That is quite odd. Then, okay. Let's try to tackle the next one then. Is it okay? Ready? Okay. I'm going to give you this question. X to the 4th power plus 4. If it's minus 4, I know that you know how to factor. Do you see what I'm saying, guys? But what if I have x to the 4th power plus 4? At this point, the way I wrote it, some of you guys might know how to factor this one. Actually, so my original question is this. It's not this equation, but rather, my original question is factor x to the 4th plus 4. That's my original question. And I'll be using this one. Is that clear, guys? How do you factor x to the 4th power plus 4? All right. I should give you about a minute for you to think about it. And this is such a popular classic question in honors class / research honors class level. So therefore, I'm sure you've seen it one time. Because I know that I do talk about this question, and we talk, the teachers, we do talk about that question. So I know that you guys have done it one time. But I don't blame you if you forgot, because it's a little bit special kind of factor. But one way or the other, can you factor that function? Yeah? Okay. So I'm going to give you about a minute for you to think about it. Alrighty. If you have an answer, just shoot it over to me, guys. Of course, I know that you can do this one algebraically, which I'm going to show you a little bit later. But also, we're going to try to do this one using complex numbers as well. Alrighty, guys. So, among many ways, what I'm going to do is I'm going to be using the complex numbers. How are we going to do that? First, I realize that x to the fourth power is equal to what? Oh, that's equal to negative 4. Is that clear, guys? But what's negative 4? If you remember, negative 4 is right over here. Can you see that, guys? The r equals 4. And then angle theta is equal to 180 degrees. So I'm going to say it's going to be 4 CIS 180 degrees. How about that, guys? Is that okay? Then what is x? Oh, I have to take the fourth root of 4. What's fourth root of 4? That's the square root of 2, isn't it? And then what's the first value? CIS. Oh, 180 divided by 4. What is that? 45 degrees, is it? Is that clear, guys? All right. That's 45 degrees. Now, but I would have added 360 for the next value and divide by 4. But if you add up 360 degrees and divide by 4, that's in fact equal to 90 degrees. So what I'm going to do is I'm just going to add 90 degrees next time. So x of 1 is equal to this one, then x of 2 is equal to radical 2. CIS, what? 135 degrees. Next one will be what? Radical 2. CIS, what? 225. And then the last one is what? Radical 2. CIS, what? 315. How about that, guys? Are you guys good so far? And then these angles are quite nice because they're all 45 degrees. That's the angle right between each quadrant. It's quadrantal angles, essentially. So let's look at the first one first. If I were to look at x of 1, I get to see that my first angle is 45 degrees. Let's assume there's 45 degrees here. Is that clear, guys? Yeah? And then this length is equal to radical 2. Can you tell me the length of x and y? Come on, yes. Square root of 2? No. Yeah. It's 1 radical 2, isn't it? 45, 45, 90 triangle. 1 radical 2. Yeah. 1 radical 2, isn't it? So in fact, this particular point becomes, guess what? This point becomes, it's the what? 1 plus I. That's the first point. Is that clear, guys? Then what are the next set of values? I'm going to try to draw the circles so they're making sure that length is all the same. Okay. My next one will go 135 degrees is right over here, isn't it? In the middle. And once again, 135 gives me this one is 45-degree angle. And this length is still radical 2. Then what do you realize, guys? Here, this particular point represents x is now what? Instead of positive 1, it's going to be negative 1. So can I say negative 1 plus I? How about the third one? 225. In fact, 225 is right over here. And guess what, guys? This point becomes negative 1 minus I. The last one comes down through this way. What happened with this one, guys? It becomes 1 minus I. Can you guys see that? That will be 315 degrees. If I know that, then what I can do is this. These values are the 4 roots. So what I can do is I can actually do the linear factorization. Linear factorization, once you know the roots, is rather simple. You just have to do x minus each one, x minus that one, x minus that one, okay? So linear factorization in this case would have been x minus 1 plus I, x minus 1 minus I. I went these two first. And then x minus 1 plus I, but minus. Wait a minute, I have to put down another negatives. I need space for that. 1 minus negative 1 plus I. I did the second quadrant one. Last one is what? X minus negative 1 negative I equal to 0. That's what I could have done. I just did a linear factorization, isn't it? Now, wait a minute, guys. These are conjugates of each other, isn't it? Can you say these are conjugates of each other? So what I could have done was I could have multiplied just like what we talked about earlier. I could have multiplied these two factors the way that I have done earlier, which is this way. Making that into difference of squares. Is that clear, guys? Or another thing that I can do is this. I remember from last year. Do you remember that if I have ax squared plus bx plus c equal to 0, remember sum is equal to negative b over a and product is equal to c over a? Yeah? And then if you're to do this one, if you know the root, then you can actually use this idea to come up with an equation. Remember that, guys? Now, then here, what are the sum of the roots? Sum is equal to 1 plus I plus 1 minus I, which is equal to what? 2. What's the product? 1 plus I times 1 minus I. What is that equal to? Oh, that's equal to 1 minus I squared, isn't it? By difference of squares. That's equal to 2 as well. Oh, so this becomes sum is 2, product is 2. Then what is the equation that I'll be getting out of this? x squared minus 2 plus 2. I mean, minus 2x plus 2. I mean, this is all something that which you guys have done last year. Knowing two roots, you come up with the quadratic equations, right? How about here, guys? Now, in this case, what can I do? Sum is equal to negative 1 plus I plus negative 1 minus I. And what is that? What is that equal to, guys? Negative 2. Sum is equal to negative 2. And then, how about the product? Product is equal to negative 1 plus I times negative 1 minus I. Once again, this one becomes what? Negative 1 squared. First one squared minus what? I squared, isn't it? Did you realize that this is still equal to 2? Then what does this one becomes? X squared plus 2x plus 2. Oh, since I made my coefficients of x as a, rational numbers, I guess I can call this one as my factoring then. Because my original expression here can be expressed as product of these two. So what I can say is x to the fourth power plus 4 is in fact equal to x squared minus 2x plus 2. And next one is what? X squared plus 2x plus 2. That will be my factoring. Let me show you the full page. It's kind of short, small. You know what? I'll do this one. And I'll do the two screen. I'll go down to the next screen soon. And you get to realize that, working with a complex number, especially with whole representation, using the De Moivre's theorem, it allows us to find the nth root of a complex number. And then in that case, since it gives me the individual root, what it helps us to do is it helps us to factor the linear, it helps us to do the linear factorization, which helps us to combine the things and simplify, hence able to get the regular factorings. Now, some of you guys might be wondering, Mister, there's got to be some way for us to do this one without using this. Yes, there is. What you guys have learned last year was this. If I have x to the fourth power plus 4. Now, many times, memorizing expressions and formulas gives us insight. That's why I always say, more you memorize, more you recognize. As always. I think I might have given you this one, didn't I? Did I mention the? Let me just put it on the side. Did I mention this one right one time? Do you remember I talked about 11 squared, 12 squared, 13 squared? Expansion and then, making an association and memorize? Do you remember that by any chance? I don't. Oh, you don't? No, I don't remember that. You do remember that? No? No? Okay. Watch this one. Do you guys know that this is a regular expansion, expansion of the x plus 1 square, x plus 2 square, x plus 3 squares, isn't it? It makes sense. But one thing that which you guys get to realize is this, because I need you guys to memorize to the point where it's part of you. Watch this. If I put 1 here, what is that equal to? 11. What's 11 squared, guys? 121. What's 12 squared? 144. How about 13 squared? 169. And then, in fact, I can continue with the 14 and 15, but in that case, I have to modify a little bit, so it's not as clear as this one. Now, in your case, there's just many trivial things. If you have to memorize them, it'll be helpful. In fact, I realized that one of us was asking me about the question from AMC, like 1, 2, 2, 3, 3, 3, 4, 4, 4. That one, like in the sequence of 1 through 200, right? And finding the median number. In fact, guess what? The way that I did it was, as I was working on it, I ended up using square root of 2. But guess what? I memorized square root of 2 because I told my kids to memorize them. You know? And those little trivial things actually helps you many times. Now, in this case, why am I bringing that up? I have an x to the 4th power plus 4. Ooh, you know what? If I have 4x squared, then this one would have been perfect square. 144. Do you see that, guys? But wait a minute. If I just add something, I cannot just keep it this way because I just changed the expression. But if I subtract 4x squared, then what do I realize, guys? Did I change the expression? No, I didn't. I gave 4x squared. I subtracted 4x squared. I'm good. But wait a minute. What is this first 3 terms becomes? It becomes x squared plus 2. Perfect square, isn't it? Yeah, can you see that? How about the second one? It's a minus 2x quantity squared, isn't it? Whoa, what do I have? I have a difference of perfect squares here, don't I? So no wonder this one now becomes x squared plus 2x plus 2. And the other one is x squared minus 2x plus 2. I just changed the orders. Look at that, guys. Can you see that they are the same? Yeah? So this the one that's on the right side is the algebraic way, and one on the left side is the what? Using the complex number. You might be wondering, hey, mister, but this one looks very more complicated than this one. Yes. But this algebraic way only works in the special cases. It doesn't work for all the cases. You know? So you get to see the power of these factorings. Now, then, as a closing, let me try to get you one more question. Ready? X squared, not square. X, to the 6th power minus 1 equal to, oh no. I want you to factor this one. How do you do that? I know that you know how to do it. By what? Difference of squares, sum and difference of the cubes. Do you see what I'm saying, guys? And you have, I'm pretty sure that you already have done this one last year. You know? Why? Once again, this is one of the classic examples that we tend to do as a teacher. But my approach for this one wouldn't be just, sum and difference of the cube. We're going to use the complex. Since I gave you a value as 1, it's a bit easier for you to work on it. Alrighty, guys. Since we don't have a lot of time, I'm just going to get going. So here it goes, guys. So this, in order for me to tackle this one, I'm going to start with x to the 6th power equals 1. Because I'm going to set this one equal to 0. Is that clear, guys? Then, what is that equal to? That's equal to 1 CIS 0 degree, isn't it? So what is the 6th root? Then first one is what? 1 CIS 0. Divide by 0 divided by 6 will still get you 0, isn't it? What's the next one? 1 CIS 60. Why am I adding 60? Because there'll be 360 divided by 6. So I'm increasing by 60 here, guys. Next one is what? 1 CIS 120. And then 1 CIS 180. And then use the symmetry, but 1 CIS 240. 1 CIS 300. Lastly, but that's it. 1 CIS 360, but 360 is equal to 0 anyway. So what is this one equal to, guys? That gets you 1. What is this one, guys? Cosine of 60 first. So we get 1/2 plus radical 3 over 2 I. How about here? When you calculate this one, you're going to get 120 to the left side. It's negative 1/2 plus radical 3i, 3 over 2i. This one gets you negative 1. This one gets you, it's in the third quadrant. So I get negative 1/2 minus radical 3 over 2i. The last one is what? 1/2 minus radical 3 over 2i. And then you can follow through this one quickly as soon as you memorize the sine of 60, sine of all those things, and it'll be much easier. Now, from using these 6 values, we should be able to what do you call that? Do the linear factorization. Is that clear, guys? And then I'll be using the sum and product between these two, sum and product between these two, and sum and product between these two to figure out the rest of them. But since we don't have a lot of time, I'm going to stop here, and we'll pick it up on Monday when you come back. Have a great break, guys. I'll see you later. Bye-bye.